Hello everyone, in this video we are going to see some basic properties of factorial that is represented like this n exclamation mark, and this is called n's factorial. So the most basic property is sometimes called the expansion of n factorial, and that is something like n factorial is equal to the product of all integers from n all the way down to 1. So the product of n and all the integers down to 1. So you have to use some, I'll have to use some dots here, and then 3 to 1. Now this is only defined for n is either 0 or a positive integer. Sometimes this set is called whole numbers, but I prefer to write it this way. So the factorial is only defined for 0 and 1 onwards, all the positive integers, not defined for negative integers as such. So this is a non-expansion, but we are kind of going to see more details into it. So I'll take some real examples like 1 factorial. So n will be 1. So 1 factorial will be just 1. If n is 2, then 2 factorial will be 2, all the integers from 2 to 1. The product of them is 2. 3 into 2 into 1, 6. Then n is 4. 4 factorial equal to 4 into 3 into 2 into 1. So I'm just taking the previous result and I'm multiplying with the next integers. I took 1, multiplied it with 2. I took this result, multiplied it with 3, give me 6. And I took 6 and multiplied it with 4 to get 24. So I can keep on doing this. So one of my favorite ways to start problems is to kind of start writing down the examples with real numbers, with actual numbers instead of just alphabets, because this helps you visualize what's going on. So these are some standard basic factorials, but that's something we compute numerically. Over here I'm going to talk more about the properties or some more theoretical background of factorial and a bit more formal definitions, not just these numbers, because this is something we already know, this is standard. And what I'm going to talk about is, and this, by the way, this doesn't define what is 0 factorial. That's another famous problem in math, is people speak a lot about zeros factorial. Well, it is 1, like you might already know it's 1, but there's a lot of debate or confusion sometimes about why is 0 factorial is 1. If you go by this definition, then I said I'll multiply n with all the integers lower than n all the way up to 1. So what happens for 0? Because 0 is already less than 1. So with this definition, you won't be able to define 0 factorial. That's another problem, another reason why I'll look at more properties rather than these numbers. So I'm going to define a gamma function. That is a very standard famous function, but I'll keep it simple. I'll not really explain the integral calculus part of gamma function, but I'll just write down the property. So this is the gamma function. So gamma n plus 1 is equal to n factorial. This is just a property of the gamma function. I'll not be proving why this happens because this will need another dedicated video on the gamma function itself. And gamma of 1 is 1. This can be proved by integral calculus. And the other property is gamma of n plus 1 is n times gamma n. Over here we are just taking these as facts, although all of this can be derived from the definition of a gamma function. But I wasn't talking about gamma functions here, I was talking about factorials. But it so turns out that if we use gamma functions, it's a bit easier to explain the properties of the factorial. And that's why I brought it in, to give ourselves new perspectives, kind of. So if this happens, then as I wrote here, the left hand side here will be n factorial is equal to n times. So if n plus 1, gamma of n plus 1 was n factorial, gamma of n should be like subtracting minus 1 from both sides. This becomes gamma n equals to n minus 1 factorial. So there you go, there you have it. You can see this pattern, like if we further repeat this for n minus 1 in this way. Then we can combine all of this and we keep doing this up to, let's say, 1, and then we combine these results. So 1 factorial will be 1 times 0 factorial. And then I don't know what 0 factorial is. There's a problem, I've defined it as 1. But before that, what I was saying is, if we keep on expanding like this, we can easily see that we'll get this form. Okay, so we ended up with something like a 0 factorial. So how am I going to get there? If n is 0, so let's see, I said n can be 0, but here I started with 1. If n is 0, then I will place 0 here. So gamma 1 equals to 0 factorial. And I said that gamma 1 is 1. If n is 1, gamma 1 plus 1, 2 is 1 factorial. And then I write 1 factorial in this form. 1 into 1 minus 1, 1 into 0 factorial, so 1 into 1 is 1. If n is 2, then gamma 3, because n plus 1 is 3, sorry, n factorial, 2 factorial is 2 into 1 factorial. Basically just using this and this, these two, n is 3, gamma 4 is 3 factorial, 3 into 2 factorial, because n minus 1 is 2 factorial was 2, so 3 into 2 is 6. Again, I went into like actual values just for better understanding of things. I'm going to remove that part because I need space, and that's something that's straightforward to see. But I'll just end with something that's more significant to observe here is recursion or recurrence. This is the concept that's, like, factorials were just kind of meant for recursion or to define recursion. So, sorry, I'm messing up the spelling. It should be singular, I guess. Excuse me if that is wrong. There should be two R's. So I was talking about recursion. So a recursive function is something that can be expressed as a function of itself, kind of. It's used in computer science and codings and algorithms, not just math. It's very famously used in coding. So this is a definition of a recursive function, a perfect recursive function, where gamma of n plus 1 is defined in terms of n into gamma of n. But one of the fundamental things in a recursive function is that it needs to have a base condition, like it needs to terminate somewhere, so at least one value needs to be known. So every other value is known from the previous value, but when you keep on doing this, at least you have to go down to one value that has to be known. So f of 1, sorry, gamma of 1 has to be 1. I'll try to demonstrate a little bit more about how recursion works here. So this is just rewriting this, not doing anything. And hey, I can keep on writing this. So I just expanded gamma of n again in this form. Sorry, it's so I'll expand this again because I find it interesting. I mean, if you can see a pattern like I see, eventually from this we are getting here. We are getting there. We are kind of proving through gamma functions what we already know. Sounds weird maybe, but trust me, it's useful to know all of this. So 3, 2, 1, and you will ultimately get, when you're going down to 1, you will get 1 into, like here we got n minus 2 into gamma n minus 2. Ultimately, at some point, you will get 1 into gamma of 1. And that's why you needed this base condition. Because you have to know gamma of 1. You cannot go lower than this, because then you will get gamma of 0, n plus 1 is 0, then n is minus 1. That's not possible. N was defined in such a way that it cannot be minus 1. So this needs to be known and this needs to be fixed. And this is 1. How is it 1? From the integral of gamma function that I haven't shown here. But anyway, taking that for a fact, you can see that that whole thing, since this is also equal to n factorial, so this has to be equal to n factorial. So n factorial is just n, the product of n and all the integers lower than n all the way up to 1. Exactly what I had defined here. So I just did all of this to kind of defend this statement, if that makes sense. Okay. I hope this was really useful. Thank you so much for watching this video, and as always, thanks for being with me.